So let's start our afternoon session for you East Coasters with Jie Shan from Cornell, who's going to tell us about some beautiful recent work on tungsten selenide, tungsten sulfide moire superlattices. So just go ahead and take it away. And Jie, I'll give you 5 minutes warning.
Okay, great. Thank you. Well, thank you, Andrea, and the other organizers for giving me this opportunity to share our recent experimental results on the correlated insulating states in TMD moire superlattices. So first of all, I would like to thank my team at Cornell, a group of highly talented and devoted students and postdocs, particularly Eun-Ah Tang and Yang Shi for what I'm going to discuss today. And also Professor King-Fan Mak, who co-supervises the group. And of course, needless to say that the work wouldn't be possible without the high-quality crystals from the Columbia team and also from National Institute of Material Science from Japan. The theoretical support was provided by Alan McDonough and Vi Elsa, local colleague at Cornell. Okay, the moire, the graphene moire system has become a new platform to study electronic correlations by introducing new energy and length scale. And as we've heard this morning, that many emerging phenomena and even more coming out in magical graphene system. I was very fortunate to attend the original workshop organized by Eun-Ah, Cory, and Andrea in January last year, which seems ages ago, of course. So this is one of the best workshops I've ever attended, and by the way, also worth the risk of being trapped in snowstorm coming back from California. So we came home with a lot of excitement after hearing the leaders in the field sharing their discoveries. But a couple of things sort of bothered us. One is that this magic physics or strong correlation physics only occurs very near the magic angle, about 1 degree. And every device sort of is different, just like us, has different personality. So, so we are thinking, whether there's something else that can give us a wider range of magic angle, well-isolated single band, something simpler, or more robust correlation physics. And so we started working with monolayer semiconductors based on transition metal dichalcogenides. So first, let me just give a very short introduction, just a few words about this class of material. Oh, before I do that, I just want to put a few numbers together to convince you that the TMD semiconductors potentially can give much stronger interaction. So the recipe for strong correlation is to make this ratio of interaction energy to the bandwidth large. This is proportional to the mass of particle and also the spacing. So without considering the moire potential, for TMD materials, mass is on the order of half electron mass, and the dielectric constant is about 4. And for a typical moire period of 10 nanometer, you can put this number already, about 5. And then if you consider the strong moire potential, this will make, this ratio much bigger. So a few words about the material. It's a group of layer compounds consisting of transition metal, which is moly or tungsten, and chalcogenides. And in this H polytype, if you look down from the top, it forms a honeycomb, just like graphene, but with the A and the B sublattice symmetry broken. So it has been shown by us and the colleagues a while ago that in the monolayer limit, these materials are direct gap semiconductors with the lowest energy gap located at the K and the K prime points. The electron hole masses are about half electron mass. The bands are spin split by tens of millieV or hundreds of a millieV for the conduction or the valence band. And the spin of valley are locked to preserve time reversal symmetry. So monolayer TMDs interact with light very strongly. The optical response is dominated by exciton resonances. So this is about 10 years old data. So if you look at the fundamental exciton, the absorption can be as high as about 10%. And this, as we'll see later, makes optics a very sensitive probe of the system. There are also interesting optical selection rules that couple circular polarized light of different handedness exclusively to specific spin valley degree of freedom. So the difference between left and right circular polarized light absorption probes the net magnetization of the system. And this will also use a little bit later in the talk to study the magnetic properties of the system. Okay, so when two monolayers, in this case, tungsten selenide and tungsten sulfide are overlaid, they form a type 2 heterostructure. When we sweep a Fermi level, electrons first dope into WSe2 and holes first dope into WS2 layer. So when the twist angle between the two layers is small, a moiré pattern is formed. And for this pair, the lattice mismatch is about 4%, and that gives period of about 8 nanometer at 0 or 60 twist angle. And it doesn't change sensitively with twist angle, because of the lattice mismatch. This significantly reduces the effect of twist angle disorder, as we have seen in some of the just the bilayer graphene system. And then the long wavelength moiré potential causes Bragg diffraction of electrons and leads to moiré minibands. And here I'm only showing you the set, the lowest energy conduction and valence moiré minibands. Okay, so let's just quickly compare the two moiré systems. So because the bands are topologically trivial in TMDs, so linear orbitals can be constructed, and this is different from what Ashwin talked about in the graphing system. The moiré potential is stronger, so that gives you more confinement of charges, and this gives you a strong correlation. And also, instead of requiring 8 particles to fill this band, we only need 2 particles to fill the first moiré miniband because we only have spin valley coupled degree of freedom. And then, of course, we don't require magic angle. There is a pretty wide range of twist angles that will give you strong correlation effects. And it has been shown by Alan McDonough and colleagues that the holes, which also turns out to be true for electrons in such a system, provides realization of the single band Hubble model on a triangular lattice with 2 parameters. The on-site Coulomb repulsion is calculated to be on the order of tens to hundreds millieV, and the intersite hopping parameter T is somewhere between 1 and 10 millieV, And the hopping parameter decreases exponentially with decreasing twist angle. So this gives you a knob to tune the U/T ratio. Okay, so quickly about sample and the device fabrication. We use pretty much a similar technique as twisted bilayer graphing. Exfoliate single layers and stack them. Using optical techniques, we can determine the crystallographic orientation of the monolayers, and we can stack them accordingly. Alignments usually can be done with pretty good precision, like ½ degree-ish. And this is like a typical device. We have the Moire system encapsulated by HBN and very thin graphite gates, which can penetrate, light can penetrate through. So for optical measurements, we have spatial resolution on the order about 1 micron, and then you can also do transport or capacitance measurement at the same time. Okay, so first I would like to focus on what's happening when you dope one particle per superlattice site, and that's half filling of the first Moire band. And this is in-plane resistance as a function of a filling factor at different temperatures. Okay. At low temperature, you see there are two prominent peaks at the filling 1 and the filling 2. Let's first ignore this very low filling part when the contact resistance goes up like crazy. So when you, increase temperature, those peaks sort of gradually disappear. So the peak at WS2 is pretty well understood. It's just the band insulator. The peak at WS1 is half filling of the band. So in the limit when U/T is very big, a Coulomb gap opens up, and our result is consistent with the Moire insulator picture. And from the temperature dependence of that peak, which disappears around 150 to 200 Kelvin, that gives us kind of a lower estimate of how big this U is. It's on the order of 20, but later measurements show that this is bigger than this number. So a few kind of papers sort of also reporting the insulating states at the integer filling, sort of published pretty much at the same time. One is from Fen Wang's group on the same system using optical technique. Cory Dean's group studied the twisted homo bilayer using transport technique, and also Imamogu's group at Imamogu's group studied also twisted homo bilayer using optical techniques. Okay, so now I would like to, I will get back to the magnetic property of half filling a little bit later, but now I would like to talk a little bit about the charge order states at the fractional fillings. So the we have examined the behavior at half filling using in-plane transport, and it turns out that you can also see this feature in optical absorption. So what I'm showing here is the absorption spectrum of the fundamental exciton, and then as a function of temperature, and you see this bump right at filling equals to 1, and this is correlated with the peak at in the transport. And the higher absorbance presumably due to kind of the insulating behavior and the less screening for the electron holes. And this is like a contour plot when we continuously changing the filling factor. of this peak. And then if you look carefully, you might see, there are fine features, between 0 and 1. And actually, Fenwan's group used the optic technique to probe the charging dynamics into the Moire superlattice. And in the resistance channel, they were able to identify peaks at 1/3 and 2/3. And they assigned those two states to generalized Wigner crystal states. So the emergence of these generalized Wigner crystal states suggests that even the intersite, the long-range Coulomb interaction is important because the particles now just are trying to avoid not just occupying the same site, but they are also trying to avoid the neighbors. So, and that tells us that the simple Hubble model needs to be modified to this extended Hubble model because the gate separation is much bigger than the Moire period. So the long-range Coulomb energy can also be significant compared to the intersite hopping. So this is the extended Hubble model. But if we consider the filling factor smaller than 1 case, double occupancy is very unlikely. Then you can just consider V and T in the model. So next, I would like to describe a new experiment in which we develop a new exciton sensing technique to study the behavior of the system for fractional fillings more carefully. So the idea is the following, the exciton in a single layer of semiconductor forms states similar to Rydberg states of 2D hydrogen atom. So in particular, the exciton excited states, 2s, 3s, and etc., have Bohr radius many times the thickness of the monolayer material. So the electric field line actually lie outside the material. Therefore, if you put something nearby, in this case, 2D electron gas, this will screen the electron-hole interaction and modify the exciton response. So in particular, if the nearby layer is metallic, this will screen the exciton interaction more significantly. Then we're going to see smaller binding energies and also smaller oscillating strengths. So that just means lower absorption absorption. If the nearby layer is an insulator, the screening effect is less, so the binding energy will be big and the intensity will also be higher. So this is a realization of this idea. So we have our sample, which is the Moire superlattice, and we place the sensor layer sort of close to it, but not that close. So we put a HBN spacer in between. The spacer is on the order of nanometer, smaller than the 2s exciton Bohr radius, but thick enough to kill the electronic coupling between sensor and the sample. Okay, so let's take a look at the and also the band alignment is such that when you apply gates, doping goes into the sample and leaves the sensor always neutral in this case. Okay. Okay, so let's take a look at the result. What I'm showing here is a counterplot of the 2s exciton resonance in the sensor. So the y-axis is the exciton resonance energy, and the color shows the intensity of the absorption. So blue means high absorption and the red means low, okay? And the x-axis is the gate voltage, which changes doping. Along this direction, we add electron into the system, so they go into the Moire miniband of WS2, and then negative gate voltage, we dope holes into the WSe2 Moire band. So we see many peaks, at different energy and a different intensity. So the highest 2s exciton energy occurs at the 0 gate voltage, and this also has the largest intensity. And this is the gap of the superlattice. Okay, that's the largest gap in the system. And we also see, this enhanced feature at μx1, which corresponds to the mod insulating state, and also at μx2, and that's the band insulator. And then, of course, there are also peak at the 1/3 and the 2/3, and those are the generalized Wigner crystal states we identified earlier. So anyway, we were able to see bunches of insulating states at the fractional fillings. And then next thing to do is to increase temperature and find the ordering temperature of those different states. And this is summarized in this slide. So you can see that insulating states on the electron side, and this is on the hole side, okay? So the electron and hole sides display almost identical correlated insulating states with similar energy scales. And this suggests that the same correlation effect is in play. And in general, the states on the electron sides seem to be stronger. That probably can tell us about, the U/T ratio for the two different bands. And in the limit when the bandwidth is 0, we expect the states to be symmetric about half, because half fill and half empty should be identical. But here we see a little bit different. And that also tells us that, quantum effect, the T, is somewhat important, and it's more important for the whole size. I think I lose some time. I probably should.
Yeah, maybe 3 or 4 minutes if you want.
Yeah.
But
okay.
Start to wrap up.
So let me just skip this quickly, and I would like to talk about magnetic properties. So anyway, so there are some quantum effects, but let me leave it here. And also, if you look at some of the fractional states, so for example, half and 2/5, they explicitly break a rotational symmetry. And you can also use optical techniques to probe the anisotropy, and this is described in this paper. But I would like to skip this and talk about the magnetic properties. So the ground and low energy excited states of the mod and are determined by interaction between localized magnetic moments that survive charge localization. To gain insights, so we would like to study the magnetic interactions. And so we measure the magnetic susceptibility, and the way we analyze this, because we cannot see the ordering, right? And it's like analyzing the high temperature data. So in this kind of a simple mean field model, if you look at the susceptibility at a high temperature, it diverges at the 0 temperature for paramagnetic material, diverges at the positive temperature for ferromagnet, and diverges at some negative temperature for antiferromagnet. So it can be described by this simple Curie-Weiss law, and where this constant C, is proportional to the sample magnetization, and this theta gives you, the type of interaction and the energy scale. So you can do 1 over chi. So I told you that by looking at the difference between left and the right circular polarized, the absorption will get the net magnetization, and from there you can, get the susceptibility when you apply small magnetic field, and this is the result. So the susceptibility, indeed, follows some kind of a Curie-Weiss law, and this is for nu equals to 1. The analysis tell us that the Curie-Weiss temperature is on the order of half Kelvin. And this is consistent with super exchange mechanism. That's the second order process. This temperature tells us about the exchange energy, J. So we got the U is on the order of 100 millieV, and so this is half Kelvin, which is 0.05 millieV, and that gives us the bandwidth about 2 millieV. This is consistent with the band structure calculations. So pretty much at this point, this is given by, can be described by Heisenberg model, right? And we can do the same measurement for other fillings. So near nu equals 1, we have, so let's look at the red dots, okay? And that's the effective, the Curie-Weiss temperature, and it's in negative theta. So those points are positive theta, so it's ferromagnetic-like, and those points are negative theta, so it's antiferromagnetic-like. So right at 1.2-ish, there is, change of sign. At the same time, the susceptibility diverges. So this possibly tells us something about, quantum critical point or so. And this is like an initial result. And after that, we look at what's going on for the fractional filling more carefully. And this is more careful measurements. And you can see that, the antiferromagnetic interaction sort of very, very weak for small filling. That's sort of understandable because, the particles are far away from each other. And then it also goes down close to 1 because at that point, the mod state settles in. And in between, some kind of a peak, but surprisingly, we saw a very large dip right at 2/3. So what's going on here is that, so if you look at this, it's the Wigner crystal state, right? It looks like this. The particles, occupy kind of the hexagonal pattern. So there are two possible kind of exchange pathways. One is the super exchange, right? Like what we talk about for Mars states. And that gives us, theta on the order of half Kelvin. But there's another channel. So for example, this particle can hop into the middle empty seat. And then, this guy can take over this seat, and then this can go back. So effectively, by doing something like this, those two particles have already complete exchange. And this, the potential energy involved is V instead of U. So then you can get a little bit higher interaction energy. But there's one caveat. If you do this carefully, if you sum up all the possible hopping channels, this term actually disappears, and then they all cancel, and it gives you the next order, which is multiplied by small parameter t over v.
We better wrap up pretty soon.
Yes. Yeah, I'm about to. Okay. So, but in this case, you know, we think that we don't have perfect triangular lattice, and the cancellation is not complete. So it's mostly this energy with a little bit of a cancellation, and that explains, you know, what we saw in the experiment. So basically, what we saw here is competition between charge order and you know, the antiferromagnetic exchange. And then to test this, you know, of course, you need to kill the charge ordering state. And we do this by putting kind of a metal very close to the system to screen out, you know, the long-range cooling interaction, and then indeed, you don't see this dip anymore. So I'll wrap up. So the semiconductor Moire system provides kind of an alternative or a new platform to study correlation. It's different from graphene. Extended Hubble model on triangular lattice is a good model for the system. We've seen a few interesting things. And then, of course, you know, the system is very rich, and we are at very early stage. There are some other open questions and also challenges, you know, for this particular system. So I'll stop here and be happy to take questions.
I'll clap on behalf of everybody. So if you have questions, please just go ahead and raise your hands. We'll start with Arup, and you should be able to talk now if you unmute yourself.
Hello, hi ma'am. I have one question regarding the energy versus gate voltage plot. So hello, can you hear me?
Yeah,
yeah,
energy
we can hear you.
Versus
energy versus the gate voltage plot. Yeah.
Slide 21, I think.
Yeah, slide 21. Yeah. Yeah, so why there is this V-like shape appearing near the insulating steps? Is there any particular reason for that?
Okay, so the question is about this shape.
Yeah,
Okay.
yeah. Exactly.
I didn't get into details about the excitonic interaction in semiconductors. So, you know, this is like the response of exciton to like to the electron gas. So they form some kind of collective excitation. You know, people use the term of porons. So you can have, you know, different collective excitation. And what we are seeing here actually is this, you know, poron, one of the poron branches, you know, we are seeing it. So it's the electron hole plus the electron C. It's the collective excitation, and then you can analyze, you know, more carefully, you know, about the interaction between the electron hole and the 2D electron gas in the nearby layer.
Okay, so it's like a new kind of state is appearing from those insulating states. Is it like that?
Yeah, you can think it that way. Yeah.
Can it be that there's a you know, that the charge density wave is sort of pinned at integer filling, and then you have something slightly incommensurate as you dope away that keeps the same type of order before recrystallizing? Is that, did I understand? Is that the answer or that you gave? Or?
So I probably didn't answer this very clearly. So what we are seeing is the exciton response from the sensor layer. Okay. And then what we are doing is trying to increase the doping density in the sample layer, okay? And then, you know, in the when the sample layer is neutral, you see this feature, right? And then when you increase the doping density in the sample, and that's just you know, in this case you can think of it, you know, 2D electron gas in the sample, and that will dress the exciton in your sensor, and this is, you know, part of the signature of that dressed exciton in the sensor layer.
Right. I guess since I don't see any other hands raised, I'm going to keep asking this question. But if you have other questions, please, everybody, raise your hands. But if let's say I ask the question of what is the ground state of the 2D electron gas that you're trying to probe at, you know, 0.2 volts of V gate, or you know, maybe half a volt of V gate inside this parabolic feature. Should I think of that feature as indicating maybe there's an incommensurate charge density wave that's only stable, you know, is it a Wigner crystal basically that then is only stable up to some filling before it destabilizes to something that discretely breaks the symmetry?
Okay, so for this discussion, maybe it's better to move into this Wigner crystal states, right? So we know that this guy and this guy are Wigner crystal states. And then, you know, if you, I'm talking about zero temperature limit. Of course, this experiment is not at zero temperature. So at a zero temperature, when you put in more charge, what's happening is that, you know, you get into the mixture of different, you know, so you know, so first of all, when V is much larger than T, you know, we get the Wigner crystal states, right? So when V is not much larger than T, then you can get the charge density wave, you know, because the modulation of charge density is reduced from the Wigner crystal. And then the question is, what's happening in between, for example, you know, those insulating states, and that's kind of a mixture of, you know, the different charge order states. Let me put it that way.
So maybe quick questions then from Charles and then from Oscar.
Yeah. So at these half-filling states that have the stripe order that you guys mapped in another data set,
yeah.
You guys discussed a little bit how on repeated thermal cooldowns the stripe order rearranged into new sets of domains, more or less freely, spontaneously. So that sort of indicates that order is spontaneous and not really pinned to strain in the lattice or anything. Have you guys tried any techniques for biasing towards one stripe order, like trying to cool down with strong polarized light or anything like that?
The quick answer is no. We are trying a different measurement, you know, for example, if you can intentionally put in kind of a uniaxial strain and see how that changes. But we don't have any new data to show.
Right. Thanks.
Oscar then?
Can you hear me?
Yeah.
I have a question about the last part of your talk. I'm just trying to make sure I understood the picture regarding the dip in theta. So is it true that you're saying that there is a particular form of an insulator where, because of some cancellations, a contribution to the exchange is gone, and so you only have the nearest neighbor exchange, and if you either melt this insulator or you dope away from it, then you recover the additional contribution to exchange. That's why theta would go up.
Yeah. So our current understanding is that the charge ordering competes with the antiferromagnetic exchange, and that's why the antiferromagnetic interaction, you know, the exchange energy is low at this particular filling to 30.
Because there you just get the nearest neighbor contribution.
Yeah, because all the, you know, the charges are pinned down, right? Because of the.
But you have two contributions, right? So you have the top picture and then the bottom picture. The top
so
picture
the top
is still good.
Picture give you, it's always there, yeah. So this picture gives you something lower energy. So, you know, if I put this point on the graph, it will be somewhere here, okay? And what we measure is a few times larger than this.
Mm-hmm.
So if you naively just have, this type of hopping, you can have T squared over V contribution. And
Yeah.
that energy is a little bit bigger than what we observed here. So what I was saying that if this is a perfect triangular lattice, and if you add all the, because I'm showing just the one possible channel, right? But if you can come up with all the 180 different, combination of this hopping, this, and that, add all of them together, they actually cancel. And this is done by my colleague, by Elsa, by the way.
Right. So then when you bring the screening layer close, you presumably get rid of the long range part of the Coulomb interaction and therefore destabilize this particular insulator.
Yes.
Right?
So yeah.
And so why does the theta go back up? Is it now these processes are no longer canceling?
So you if you make a V goes away, so the charges are no longer pinged. So you can just so you can just think of this picture as itinerary magnetism. That's what's going on.
I think we better cut this discussion off now and move on to the next talk so we don't get more than 5 minutes behind. But we will have a longer period for discussion after this next talk where we can revisit some of this. So let's thank Jie again in our hearts, if not audibly.